Hey Brian, seen you for a while.
Yeah, not all summer. We never saw each other, I
Yeah,
guess.
you were here
Yeah,
and in and out. Yeah,
yeah. Still a sort of a cooped up year, I guess. New,
totally.
new COVID habits.
That's right. I'm in a perpetual seminar the whole summer, so
Yeah, well, that's cute. That's fun. Yeah, there you go. But you're sitting sideways weirdly in the
it is.
first.
Yeah, I don't know. My orientation is. I need a slanted desk to compensate for my slanted screen.
Yeah.
Oh, okay. Sorry, Tracy, I missed that. So, welcome to the seminar, CGD seminar. So I'm filling in for Dan, who unfortunately is a little under the weather this week. So get well soon, Yang. Yeah, get well soon, Dan. Really excited to introduce Yang Tian this week. So Yang comes to us as from a postdoc at Livermore, and I'm particularly excited because she is a new scientist within the atmospheric modeling section here in CGD. So Yang got a master's from Yale and a PhD from Harvard in 2018. She has a really impressive resume with work on cumulus dynamics, large eddy simulation, really innovative Lagrangian approaches for determining cloud entrainment. This is really, a critical component of convective parameterization. that is often poorly constrained. There are many, many other scientific areas in which she has a really good presence: machine learning, stochastic scale aware parameterization, land atmosphere interactions, cloud feedbacks and sensitivity, data assimilation. So she, good for us. It's great. She brings this wealth of experience to bear for CAM development within CGD. And so today, seminar title is there: Understanding Convection Environment Interaction from High-Res LES Modeling and Observations. So take it away, Yang. Thanks.
Thank you so much, Rich. Can you hear me fine?
We can, yeah.
Okay. Let me share my screen. Okay. Can you actually see my screen?
I think it's coming up. Yes, we can. Yeah, great.
Does it?
It looks good. Yeah,
Okay,
we see the title.
Good morning, everyone. So today I'd like to discuss my work on the interaction between moist convection and environment from both high resolution LES modeling and observations. Sorry. Good. Okay. Can you actually see like my second slide?
I cannot. No, it's still the first slide. Is it a PDF or a PowerPoint? Can you hear me, Yang? Oh dear. Oh no. Oh. Can you try again, Yang? We kind of lost your screen there. Yeah. Okay. Try one more time for the full screen. Yeah. Do you want to just? That's it. Great. It's flicking now. Great. Go for it. You're on mute, Yang. Sorry, you must have put yourself on mute by mistake.
Okay.
Great. Can hear you.
Okay.
Hi, Yang. This is Tracy. Sometimes if you turn off your video, it helps with your bandwidth. So you might want to give that a try.
Okay. Okay, I will do that.
Yeah, it's worth it. Yeah.
Okay, does this work better?
We can hear you. Yeah, sounds clear. Good.
Okay. Can I? I'm so sorry. The internet is really poor. Okay, good. So before I get started, I just want to introduce a little bit more about what I have done in the past. During my PhD, I actually have worked extensively with using idealized modeling to understand the interaction between moist convection and environment, and develop like related theories about this interaction in the hope that we can use some of those theories in the climate model development. And during my postdoc, I have looked at a lot of observations, and we try to use those observations to validate my earlier theories, at the same time to answer some important questions in the climate and convection community, such as the mechanisms behind convective upscaling, like convection aggregation, and also the controlling factors of diurnal timing and intensity of precipitation. So at CGD, I hope to combine my knowledge in both high resolution LES simulation and also observations to contribute to the latest development of CAM7, in particular in convection representation. At the same time, I hope that some of the tools that I have developed in the past can be potentially helpful for the collaborative efforts in other areas at NCAR, for example, like land atmosphere interaction and also extreme weather forecasts. Okay, Now let's come back to the research. Rich, can you actually hear me fine at this point?
I can hear you, and the slide is on moist convection and its interactions. Is that right?
Okay, great. Yeah, if at any time you can.
Yeah. I'll jump in. No worries.
Yes. Okay. So why do we even care about the interaction between moist convection and environment? Because cloud processes are at the center of coupling different climatic processes. It also plays a very critical role in Earth's radiation budget and the global hydrological cycle. However, we know that a typical climate model is wrong at about 1/4 to a degree, which is too coarse to resolve those small-scale cloud processes. Therefore, we need to rely on what we call by convection parameterization to include the collective effects of cloud on their large-scale environment. And this parameterization is dependent on a statistical relationship that describes the interaction between clouds and their large-scale environment. Here, like the figure on the right, if you cannot see my mouse, the figure on the right, it shows the simulated precipitation by exactly the same climate model, but just with two different convection parameterization schemes. We can see that the simulated zonal mean precipitation is actually completely different from one another. This is just to demonstrate how sensitive the simulated climate circulation can be just due to the different choice of convection parameterization scheme. Therefore, we really need to better understand and simulate this interaction in climate models. This talk consists of a few different sections. I will primarily focus on using high-resolution LES modeling and observations to understand different aspects of convection environment interaction. And we'll briefly mention about a machine learning project that I recently participated to correct model bias in precipitation. So as Rich just mentioned, entrainment mixing is one of the key processes in the convection environment interaction, which is basically the turbulent exchange between clouds and environment in terms of mass, momentum, moisture, and heat. Therefore, it strongly impacts on the vertical distribution of heating and moistening, the resulting large-scale circulation, as well as the chemical and pollutant transport. Earlier research have proposed different formula to characterize this entrainment mixing or entrainment mixing rate, which can be related to cloud radius, vertical extent of cloud height, relative humidity, buoyancy, vertical velocity, etc. However, most of those earlier proposals are empirically based, were from lab experiments. Therefore, they have not been subject to rigorous tests yet. One difficulty about those tests is that the entrainment mixing is very difficult to measure in observations, and we do not have sufficient amount of observation to validate against those formula. Another difficulty is that multiple factors actually interfere at the same time to this entrainment mixing process, making the statistical inference rather difficult. So to overcome those above mentioned obstacles, we designed a new analysis framework based on Lagrangian particle tracking, high resolution LES modeling, and a linear response function to understand the controlling factors of entrainment mixing. In particular, we try to disentangle the relative contribution of each factor in contributing to this turbulent mixing process. To start off, I will just go with a relatively simple case that is a shallow convection case. Now, I'd like to walk you through those different steps in how to design this unique analysis framework. The first step is quite easy. It's just to get clouds. I use a large Eddy simulation SAM to simulate shallow clouds from Bomax Field campaign with 50-meter horizontal resolution and 25-meter vertical resolution. And I use a temporal resolution of 1 second. For those of you who are not very familiar with large Eddy simulation, you can basically think of it as a type of numerical simulation that resolves the largest eddies in the system that carry with them the most turbulent kinetic energy. Because we cannot experiment with the real clouds, the LES simulated clouds can be thought of as one that is as close as possible to reality. Therefore, we can experiment with these virtual cloud fields and infer what is happening in reality. Okay, after we get this virtual cloud field, in the next step, I release tens of millions inside this entire domain, combining the partial with field, it can change clouds and we tens of millions of particles into the main field. We sample those tens of millions of particles and we
Yang, can you still hear us? Did we lose her? Can you tell, Tracy, whether we lost her or not?
Yeah, she's not in here, but
Well,
she's back.
oh, she's back. Okay.
Am I back?
You are.
Can you hear me?
We can, yeah, I'm not quite sure. Yeah, let's just keep going. Otherwise, I think, yeah. So we can see your slides. Yep.
Okay.
Go ahead.
Okay, you can see the slides now.
Yeah, I can.
Okay. Then comes to the question of how can we statistically sample those tens of millions of particles and then calculate the entrainment rate in a meaningful way. We define a framework that is a spectrum plume representation as what has been proposed by Arakawa and Schubert, 1974. By adopting this spectrum plume representation, we can actually much better review the in-cloud heterogeneity, which is critically important for the nonlinear microphysical processes and cloud aerosol interactions. And by summing up all of those subplumes, it can actually recover the bulk plume property, which is the most commonly used cloud model in current convection schemes. Then we designed a parcel grouping algorithm to cast those particles into this spectral plume representation. So first, we sample all the particles that are within cloudy updraft at the cloud base. Then we record the determined heights of each of those cloud-based particles and divide different parcel groups or to different. So 100. So each parcel group, parcel property homogeneous and different among different parcel groups. And the last step, not only sample the cloud-based particles, but also and to their respective parcel group based on their ultimate determined heights and calculate entrainment rate by counting the number of particles that go from environment into the cloudy updraft. And here is the result. Here, this figure, it shows the fractional entrainment rate as a function of parcel group number and vertical height. The larger the parcel group number, the higher the determinant height is. And we can think of each parcel group as corresponding to one plume in this spectral plume representation. By using this spectral plume representation, we can see that the entrainment rate, it differs among different parcel groups, varies as we actually fully review. Okay, now we clouds, we release tens of millions of particles, and we cast those particles into plume representation and calculate the entrainment rate each parcel group. But we haven't answered the question as to what are the controlling factors of this entrainment process. This is achieved by introducing a linear response framework. In addition to the control simulation that I just introduced, I also created a perturbed simulation by adding a very small amplitude temperature perturbation in the free troposphere. And I repeat step 1, 2, 3 to obtain cloud statistics for this perturbed simulation. By comparing the cloud statistics between my control and perturbed simulation, we can get the change in entrainment rate due to this imposed temperature perturbation. And the rationale behind this linear response function is that in this linear framework, the fractional change of entrainment rate should be linearly represented by the fractional change of its controlling factors. Okay, let's see how it works. Now that if we just zoom into one single parcel group or just one single quantile, we can see that the fractional change in entrainment rate, which is represented by this solid blue curve, can be very well represented by the linear combination of the fractional change in the vertical velocity and the cloud radius, which is represented by this dashed blue curve. And this relationship still holds if we did the same calculation for all the parcel groups as shown by the figure here on the right panel. And based on this linear relationship, we can actually derive a new entrainment formula. That is, the fractional entrainment rate is inversely proportional to the product of vertical velocity and cloud radius, scaled by a turbulent velocity constant alpha. So this newly proposed entrainment formula, I believe, is already implemented in one of the MYNN EDMF convection scheme in WRF to improve the shallow convection representation. And I hope to see like more results from the study. So in this fractional entrainment formula, we can see that vertical velocity is an important contributing factor. It is a direct measure of convective strength. It also has a strong influence on the cloud microphysics because it determines the aerosol activation rate. And also high velocity is often associated with severe weather such as hail, lightning, thunderstorms, etc. Therefore, a physical representation of in-cloud vertical velocity can allow for a much tighter coupling between cloud microphysical and dynamical processes. At the same time, it can also help improve like the extreme weather forecasts. Given the importance of vertical velocity, current convection schemes have actually adopted like a velocity parameterization. So the first equation is actually the vertical momentum equation for the steady state plume. And the second equation is the most commonly used velocity parameterization equation. So what it does is to combine the first two terms in the velocity equation into an effective buoyancy term by a virtual mass coefficient A, and also combines the last two terms, which is the dynamical perturbation pressure term, and this is the entrainment drag term, into another term with the coefficient B. So what are the problems with this representation? Two critical issues here. The first is that it is actually not clear that the last two terms are linearly related to each other. So I actually don't know what this B coefficient represents. The second issue is that we can see that the A and B coefficients, they can vary by a factor of 3, depending on the different cases and different scenarios that you look at. So this is actually not very ideal if we want to use this for forecast purpose, because we don't know coefficients A and B a priori, right? So the question here is, how can we faithfully represent the abstract vertical velocity, in particular the perturbation pressure terms, without having to rely on arbitrary coefficients A and B? Again, we resort to the new analysis framework that I just introduced. And after examining the relative importance of different terms, proposed that this is the most reasonable representation of the parameter. And in terms of perturbation pressure terms, we can actually solve Parcel equations to numerically solve those terms. We just need to have a cloud model in order to compute those perturbation pressure terms. And how to do that? Okay, this is achieved by summing up all of my previous subplumes to make a single bulk plume. And now I get my puffy bulk cloud. Then I will use a cylindrical 3D model to represent this puffy cloud. And I get my cartoon cloud. The only geometry is needed for this cloud base, cloud top, cloud radius, and we also need to supply a buoyancy profile, which is already in the an output in the convection scheme. And we need to make this buoyancy profile 3D so that we actually assume a 2D Gaussian distribution at each layer, scaled by the relative magnitude of buoyancy at that layer. Now that we get actually 3D profile of this simple cloud model, with this pretty simple setup and by imposing certain boundary conditions and assuming non-divergent axisymmetric flow, we can go ahead to solve those Poisson equations numerically. And here is the result. So this figure, it shows the virtual mass coefficient from both my LES model and my cartoon model. We can see that given the simplicity of my cartoon model, it can actually do a pretty good job in reproducing what we can see from the LES model. It is also worth pointing out is that the virtual mass coefficient is not a constant. In particular, if you have a localized perturbation in the atmosphere, it actually varies as a function of height, depending on the vertical stratification. But we don't need to actually impose like a constant. We can actually compute them directly. Similarly, like our cartoon model can very well capture like the perturbation, the dynamic perturbation pressure to a good extent, even though like not the details. Okay. So in summary, we designed a new analysis framework based on Lagrangian particle tracking and high resolution LES modeling. We proposed a new entrainment formula and a new deterministic model to compute the in-cloud vertical velocity. I didn't mention that because I just want to show you how it works for shallow convection. We have also done that for the deep convection, and the relationship of the entrainment rate still holds in the deep convection case. So this proposed entrainment formula together with the velocity parameterization has the potential to be used in the unified convection scheme such as EDMF, World Club, so that we don't need to arbitrarily separate like different scales, for example, to separate the shallow convection and deep convection. Notably, this analysis framework is also very good at obtaining process level understandings in a complex interacting system. Therefore, it can be flexible to infer causal links in other systems, such as the air-sea interaction or the land-atmosphere interactions. Okay, I have showed you a modeling framework of how we understand the convection environment interaction. Later, I decided to subject those earlier developed theories to observations in the context of understanding shallow to deep convection transition. And this work is motivated by the fact that the diurnal cycle is rather poorly simulated in climate models, especially over land, which is manifested by the fact that the peak rainfall in models is generally 2 to 4 hours earlier than observations. And earlier research suggests that this deficiency can be due to like the poor understanding of or the poor simulation of a smooth transition from shallow convection to deep convection. So the purpose of my study is to use observations to understand the transition process. And I will primarily focus on Amazon region because it is a key region for the global hydrological cycle, and all the observational data are from the DOE Go Amazon Field campaign. Okay, in order to understand the shallow to deep convection transition process, the first step is actually to classify those deep regimes. I integrated a suite of ground-based, satellite, and airborne observations to classify those different convective regimes over Amazon region, including shallow, congested, locally generated deep convection regime, as well as propagating mesoscale convective regimes. So most of the regimes are defined based on the cloud top height or the echo top height. I compiled like a very comprehensive library of those different convective regime cases. So if you're interested in using any of those cases to validate against your model or your theory, please let me know and I'd be happy to share this library with you. Okay, so now we get like the shallow convection days and deep convection days. The question is, how can we disentangle the relative role of each parameter in contributing to the convective development or the transition process? Is the transition really a result of nature, which is like more related to the initial conditions at the cloud base, or a result of nurture that is more affected by the environment sphere? Decided to use those contributors. This model consists of 3 conservation.
Yeah, can you hear us?
Yeah, I've completely lost every. I don't hear her.
I think
No, she's not. She just came back in again. So let's see.
Yikes. Hi, Anne, can you hear us? I don't see her.
She's in here, but she might not be able to communicate.
Can you hear us? Okay.
Am I back?
You're back.
I'm so sorry about that.
That's okay. This is good. Yeah, just keep going.
Okay.
Yeah.
Okay, so this is like 3 conservation equations in terms of energy, moisture, and momentum. I also include some simple microphysics schemes so that my plume can condensate, precipitate, and also freeze, just like a real cloud parcel. So all the variables in this set of conservation equations come from my observations, including the cloud-based conditions and also the free troposphere conditions. So the entrainment rate that I use here, I just decided to use like the simplest representation that is inversely proportional to the vertical cloud extent instead of using my own entrainment formula because of some complications in getting the cloud radius and also like the turbulent velocity scale. So my earlier research on the vertical velocity is also used to constrain the different parameters in this momentum budget equation. Okay, so one uniqueness of this set of equation is that it simultaneously solves for the thermodynamic and dynamical evolution of the plume so that the cloud top height can be determined explicitly by where the vertical velocity vanishes to zero without having to introduce additional assumptions. And another uniqueness of this plume model is that to our best knowledge, this is actually the first time that the Doppler LiDAR measured cloud-based initial velocity is used to constrain the dynamical evolution of a plume. Okay, before we can use this plume model to understand the most important controlling factors, we first need to validate that this plume model can actually well represent the different convective regimes. And this figure shows the plume model predicted cloud top height as shown on the x-axis against the measured cloud top height by either cloud radar or the precipitation radar. Different colors represent different convective regimes. So the red is the shallow regime, and the orange is the congested regime, and the blue is the deep regime. And each dot represents one case in a specific regime. We can see that our simple plume model, it can actually quite well represent like the measured cloud top height, especially like in separating the different convective regimes. Therefore, we can go ahead to use this plume model to try to understand like the relative importance of contributing factors in determining the cloud top height. How? This is by introducing what I call a swapping experiment as used in one of my earlier research, which I just didn't have time to talk to in this talk. The idea is quite straightforward. So now we actually have like a plume and we release this plume from the boundary layer. Given the observed moisture profile and temperature profile, this plume, it can actually reach to a certain cloud top height, right? Now that if we actually change this moisture profile, this temperature profile, but keep the moisture profile fixed, this plume can go to a different cloud top height. Similarly, if we just change the moisture profile, but keep the temperature profile fixed, it will ascend to another different cloud top. Therefore, we can probe into the relative importance of all of those contributing factors by observing the sensitivity of cloud top height distribution due to the changes of those factors. And here is the result. This figure shows the cloud top height distribution after we changing one variable at a time in the free troposphere. So figure A shows the results after we replace the deep convection profiles with those of the shallow convection profiles. X-axis shows the originally predicted cloud top height, and Y-axis shows the cloud top height after swapping one variable at a time. The blue dots show the results after we replace the temperature profile, whereas the red shows the results after we replace the relative humidity profile. In general, we can see that the convective development or the cloud top height distribution is more sensitive to the change in moisture in the free troposphere compared to temperature. We can see that most of those cloud parcels, they cannot exceed 8 kilometers after we change the relative humidity, because 8 kilometers is what we use as a criteria to define the deep convective regime. And it's interesting that after we replace the temperature profile of the free troposphere, we can observe 2 distinct behaviors of those cloudy parcels. So one group of parcels, they detrain immediately right above the cloud base. And another group of parcels, they reside on this one-on-one line. Why? Because when we replace the free troposphere temperature, we actually keep the cloud-based temperature fixed. And in shallow convection days, the temperature is actually much warmer compared to the deep convection days. Therefore, we essentially create a buoyancy barrier. And those parcels, they do not have enough initial momentum to overcome this buoyancy barrier. They will detrain very quickly right above the cloud base. However, for those parcels that are lucky enough to overcome this buoyancy barrier and ascend to the free troposphere, the change in temperature seems to have very little impact on their final detrainment heights or on their final cloud top height. Similarly, the story is very similar if we replace the shallow convection profiles with those of the deep convection profiles. It is worth pointing out that if we now use a much larger entrainment rate, all of those cloud parcels will remain shallow. And this indicates that the cloud top height distribution has very strong sensitivity to the free troposphere moisture, entrainment mixing rate, as well as the inversion above the cloud base. Okay, so what about the sensitivity to the initial conditions, especially to the initial momentum distribution? To make long story short, so for this particular plume model and for our particular model configurations, we actually do not find a very strong sensitivity of cloud top height distribution to the initial momentum distribution. And because this set of equations is very similar to the equations used in the single column model in current convection schemes, so this analysis framework is actually very useful to compare the single column models against the observations. Okay, up to now, I have shown you the process level understanding of the convection environment interaction from both high resolution modeling and observations. Recently, I have participated in a machine learning project that is trying to correct model biases in precipitation in a post-processing manner. And this actually adopts like a generative adversary network that iteratively corrects the model biases in model precipitation. And the result is shown in the bottom left figure. We can see that our machine learning approach can actually very well reproduce the observed like a mean precipitation as well as like the maximum or the extreme precipitation. This similar approach can also be used to identify and also correct biases in other high resolution regional models. Okay, as a scientist at NCAR, my plan is actually to build an integrated framework that uses the power of LES modeling to understand the mechanisms of convection cloud interaction, to develop theories and to incorporate those theories into the latest development of CAM, in particular the cloud development, and to use observations to validate the results. At the same time, I plan to use observations and LES simulations to train and to validate like a deep learning algorithm that can actually
Did we lose her again?
Yeah,
She
I can see her.
is shown in the list. Let's
I
see.
see her. Hi, Yang. I think we lost you again. Oh,
She's probably
like
trying
a
to join again.
10-minute cycle of
Yeah,
loss.
I feel bad for her.
Doing great. Thanks for everyone's patience. Can see her.
Not yet.
I think she's near the end of her talk though.
Yeah.
Well, it's 11:45. So give us some time to get back on.
Yeah.
Well, it's fun stuff she's talking about, at least.
yeah.
Yeah, I like her plans. That's great. Oh dear.
Yeah, Isla says there's lots of problems with Comcast today.
Oh, really?
Yeah.
Okay,
Not
Tracy, why don't you
surprising.
advertise next week's seminar? There you go.
What?
Advertise next week's seminar?
Oh, sure.
Why not? Why are we waiting?
Let me pull it up so I'm not giving you wrong information.
She gets the. I can do it too. I have it in front of me.
Next week, we have a talk by Matt Osman. I believe he was from University of Arizona.
Yep.
He's going to discuss global climate changes since the last glacial maximum, new insights from paleoclimate data assimilation. So please, yes.
Yes. Are you on, Yang? I can't see you.
I still don't see her back in. Oh, there she is.
Oh, there we go.
Can you hear me? I'm back.
I can. We can.
Okay, did I actually finish the presentation?
No, you were on this slide and you talked about which bit. Kind of, yeah. Why don't you just, spend, what time is it now? How many slides do you have after this one, Yang?
I don't have further slide after this one.
So
I'm
why
not
don't you spend, just spend a couple more minutes, see if we can squeeze that in on this slide, 1 minute or so, and see if we can make it to the end.
Okay, so this is already the end. I just hope that I briefly introduced some of the work that I have done in the past, and I really hope to collaborate with many of you in the future in terms of developing the latest convection parameterization scheme in CAM 7, as well as using some of the tools that I have developed to understand land atmosphere interactions, air sea interactions, cloud aerosol interactions. I hope the tools can be useful for your research as well. And feel free to email me if you think I can help with any aspect of your research, and I'd welcome any collaborations. Okay, so at this point, this is it. I'm so sorry for this poor internet connection.
No problem. I mean, thanks for soldiering on through. You made good time in the end. So, any questions? See if we can squeeze some in. Yeah,
my apologies for the connection issue.
No, don't apologize. Either in the chat or I can pick them off with hands up if people want to do that. Right. Oops. Okay, Bill, I do believe that's Bill.
Yes, well, that's fascinating talk with many, many aspects. But if I concentrate on your plans to use the large eddy simulation modeling, a question I have is, do you know whether those simulations you have of the various convective regimes and plumes, whether the energetics of those plumes, what's getting converted from potential to various kinds of TKE or and various components of that, or mean kinetic energy, is that can you make sense of that? Is that got a nice kind of universal picture that you can use, and energetics of all those things are about the same, or are they quite different from regime to regime, or are they just a complete mess? How the energetics move, how the energy moves in the system. Is that understood? That's the question I have. Do you really understand that?
Still there, Yang? Oh, yikes.
Oh, was that a question, was it? Sorry about that.
She is still showing up in the list, but yeah, she might not be able
Are
to.
you on mute by any chance, Yang?
She's not.
Oh,
Yang, maybe, there you go.
oh, yikes.
We lost her again.
Let me ask Bill, why are you asking that question? You think there's some issues with that in LES, or you're just asking, just as an understanding? Is Bill interested in?
Bill's gone now.
That he was.
No, he's.
Yeah, no, the reason is that these parameterizations also do things to energetics. And one way of finding and really trying to see whether you've got, and as she talked about, all the different parameters and features, is to figure out which one is doing what to energetics. You can spend a lot of time trying to do something on a feature that doesn't do much to the energetics, and so
Right.
it guides you on what to look at and whether your parameterizations are hitting at the right energetics, basically, moving the energy the right way. And to do that, the LES might be able to tell you what those are, if you can make sense of them from regime to regime. That was why.
Okay.
See what I mean?
Yeah, that makes sense. Warcheck, did you want to comment on that, or are you waiting for a question?
No, I have a different comment. So if this subject is finished, I will start talking.
Go on until we'll wait and see if we can get Yang back on. But yeah, go for it.
Okay, but my comment is that
I'm back. I'm
Okay.
back. I didn't. I think I missed like the discussion just now. Sorry, Bill.
Did you hear any of the question at all, Yang?
Not really.
Okay. All right, Bill. Let's the Cliff Note question. Okay.
But yeah,
Yeah, just
very
quickly,
brief-
do
yeah.
you understand the energetics of the LES well enough and can characterize it well enough to really guide you in trying to determine whether the parameterizations are hitting the right parts of the energetics?
I can see
No,
you.
we lost her.
You get that, Yang? Yikes.
That was a Cliff Notes one too. So
Oh yeah.
sorry. I'm gonna leave now.
Feels like the Grim Reaper.
Yeah, Bill has the reverse Midas touch. Yang, she's still on, I guess, but
She is.
oh, we lost you there, Yang. Did you start answering?
Actually, maybe it's better that we just like type in the chat box.
So we can hear you now. So we can try one more
You
time.
can hear me now.
Yes.
Okay,
you-
we can try one more time.
You got the question? You got Bill's question? Oh my gosh.
I just hear like the mean kinetic energy, and
Yes.
that's it.
Okay, Bill. Third time's a charm.
I'll pass on it. I'll chat it out to her.
Okay, yeah, let's chat it out. And let's see if we can,
Yeah, the
let's see if
chat
we
is
get,
much better.
can we get Warcheck in? Let's see if we can get him in. Okay.
Yeah.
Yeah, so I basically have a comment. It's not a question that Yang, your approach with those particles that you follow to deduce the entrainment rate. One thing that we work on is what we refer to as Lagrangian microphysics,
Yes.
which is that you follow, let's say for the shallow convection case, you follow what we call super droplets, aerosols that get activated. So if you use that, without any cost, you get whatever you are getting from this, inserting Lagrangian particles into the simulation. So that's something to consider. And I know that this is fairly expensive, but Japanese already did Bomek's case cloud field with this approach with amazing grid lengths, much bigger, much higher resolution than what you had, like 12 meters.
Okay.
So it will be interesting, perhaps, if you want to do it, or if you want to, invest some time into this to guide them to basically do the same thing with higher resolution. I mean, I'm not sure what you will get out of it, but that's just a comment that the techniques that we kind of thinking of in LES these days, for different reasons, obviously, because there are some issues with microphysics as we do it typically, it's perhaps a better way to look at that. And you basically get it for free if you follow Lagrangian microphysics, not to mention different kind of microphysical processes that are done differently at a better level, I would say, or higher level in terms of reality. So just a comment. Thank you.
Yes. I am actually aware of some of those like Lagrangian microphysics development. And yeah, so based on this general framework, it can actually be quite straightforward to include like microphysics on the tracking pathway, and then to track like the cloud microphysical processes. Yeah, so I have actually already thought about that, but I really just haven't had time. There are just many interesting ideas out there. Yeah, I just haven't had time to really do it. But I think it can be quite straightforward. I don't know about the expense though, because currently those Lagrangian particles, they take a lot of computing power and worth of the storage space. If we go to even finer resolution, for example, like a 10 meter, the cost will like a double or even like a triple. So
yeah, but my point only is that these simulations have been done, and basically I can ask my Japanese colleagues, but I am assuming the data is somewhere and you can just use it as they have it, So anyway, but this is just a comment. The idea that you basically follow those particles, you don't have to insert anything. And of course, the microphysical reality is much different from, Bomek's. Typically people run it with, but anyway, let's don't talk about it. Let's not waste more time. So yeah, I think you know what I'm getting into. Thank you.
Yes, let's talk offline. Yeah, thank you.
Okay, we're 2 minutes till. I want to thank Yang in particular very much for navigating the technical challenges. It's a really great talk. She's at NCAR, so I'm sure you can find her email. We saved the chat. Thanks, Tracy. And so I want to thank everyone again and see you next week.
Thank you so much.
Yeah,
Thanks.
thank you.
Bye.